Hormones, hormones here and there. Hormones, 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 hormones everywhere. Hormones, 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 hormones everywhere. אנחנו מקליטים? Wee-hee-ha! There's hormones in the pancreas that help digest our food, and hormones from our pituitary make us feel real good, like beta endorphins. There's feedback loops and circuits that are beautiful to watch, and in this course we'll study them a lot, but not too much. Hormones, hormones, hormones here and there. Hormones, 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 hormones everywhere. Hormones, 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 hormones everywhere. So welcome to Hormone Circuits, Lecture 7. All good children go to heaven. Major depression. Delightful subject. Major depression, we'll talk about how we can understand major depression, a debilitating disease. Some people call it the common cold of psychiatry. It's so common, maybe 20% of the human population will get major depression sometime during their life. When I say major depression, I don't mean blues, like we all have ups and downs, feeling blue, or maybe say I'm feeling depressed. Major depression is a debilitating disease that basically makes you unable to get out of bed in the morning, to work, to have relationships, to make a living, or its most insidious aspect maybe is called anhedonia, which means lack of pleasure. So things like Sapolsky, a big researcher in the field, says major depression is a genetic and environmental and psychiatric disability that makes you unable to enjoy sunsets. And the inability to feel pleasure. And it's also associated a lot of times with slowdown in motion. So slowdown in motor. It's associated with memory defects, and it has many subtypes, of course, and we'll talk about a major subtype. There's also atypical depression. The more typical depression, there's problems with sleep, there's problems with eating, either sleeping too much or too little, eating too much or too little. And like other psychiatric diseases, there's no way to diagnose it except for a psychiatric interview, and you have to meet some criteria. I'll put it in the lecture notes. Importantly, the negative feelings and even suicidal thoughts must be present for at least 2 weeks for it to be called major depression. So it's not a day or two. And also that they can't be explained by, for example, the death of a loved one, regular mourning, unless it's been a year, or can't be explained by hormone problems like low thyroid hormone, which it can also cause depression. So after you rule out the organic thyroid problems and environmental things like bereavement, and you meet some criteria, you're diagnosed with major depressive disorder. Let's see where we are. First, we forgot to take a nice deep sigh of relief. So it's really good when we talk about depression and stress to take a nice deep sigh of relief. Welcome, breath. And this lecture links to the previous lecture on the stress axis, the HPA axis, because major depression is intertwined with stress. You can't have one without the other. It's both caused by stress and it causes stress. And the HPA axis is a major player in depression. So to review the HPA axis, as you might remember, stress is psychological and physiological stress in the brain. It makes an input we call U, that makes a brain region called hypothalamus secrete a hormone to the pituitary, makes it secrete another hormone to the adrenal glands to make it secrete cortisol. That shuts down the secretion of the two upstream hormones. And cortisol is the stress response, and an acute, fast stress response gives us energy to meet the stress, more glucose in the blood, sharpening the mind. Chronic stress, a lot of problems, diabetes, heart disease, destruction of brain areas, and also chronic stress leads to major depression, as we'll see. So HPA axis, and we also added these important interactions where the cells themselves divide. You remember 2 times this motif where the hormone that makes the pituitary secrete X2 also makes the cells grow, just like we saw in beta cells. And ACTH, that makes the adrenal secrete cortisol, also makes the adrenal grow. So, so we have this kind of slow time scale of weeks for the glands to grow. That'll play an important role in our lecture. So that's the HPA axis we discussed last time. We talked about it like an oscillator, remember, in bipolar disorder, etc. Major depression is something called unipolar disorder. There's no mania phase. It's just you stuck in this anhedonia, inability to feel pleasure, low energy, can't get out of bed in the morning. It could be for months, years, and it also could be recurrent. A lot of times there's a stress preceding it, the first few times, and afterwards you become very sensitive and it becomes recurrent even without this particular stress before. And the more times you get bipolar disorder, unipolar or MDD, major depression, the more susceptible you are to it, it seems. And it's like you become a person who has this major depression as a looming possibility in your life. It's so common that I'm sure some of you viewers know someone who has major depression or experienced it yourself, and know famous people who've had major depression, etc. It's definitely possible to have a fulfilling life with major depression, but it's also a devastating disease without really a proper understanding. And what exactly what I mean by proper understanding? We want to understand something about the time scale and dynamics of this disease. So our goal will be to understand the dynamics of depression. Now, I'll be more precise. Now, so we talk about major depression. So I'm going to pause now for some questions in chat. So I'm not going to continue until you, as usual, write a question in chat. So we talk about major depression, anhedonia. We'll soon get to the next topics. So I want to see where we are in this concept. So who's going to be brave and dare to reach the keyboard and type a question? Or comment, you can say, it doesn't have to be a question, it could be a comment, but I'm not going to continue, I'm serious. Oh, okay, there's a question. So how is this related to bipolar disorder? Bipolar disorder and major depression are 2 different diseases. Bipolar disorder has this mania phase of hyperactivity, thoughts, you take all the money out of the bank, buy some Cadillacs, give them to random people on the street, mania. And then a lot of times depression that's similar to unipolar depression. A lot of times people with bipolar are first diagnosed with depression, but once they have a mania, it's changed to bipolar. So it's 2 different diseases. People with unipolar depression have certain drugs like SSRIs that work for them a lot of times, but if you give people with bipolar disorder the same drugs, it can start a mania. So it's very important to understand which disease it is. I hope I answered your question. Okay, so bipolar disorder is about 1% of the population. Major depression, as I said, 20%, actually more in women, maybe something like 20% of women and 12% of men, if I'm not mistaken, are the numbers. So it's more in women for reasons we can discuss. Bipolar is about 50-50. All right, so I'm gonna erase this thing. I hope I got you interested in why we should care about bipolar. Now let's get a little bit more quantitative about what can we do as hormone circuit enthusiasts to understand major depression. And so when you talk to psychiatrists, they have this term called diastasis, which is to say something like a person, once they get a psychiatric disease like major depression, as if they switch to another state. From that time on, they're like a different person, and they have this fragility to the disease. And it's much easier to get into the depression than to get out of it. And also, I should say that most depression, major depression, are preceded by stress, at least in the beginning, first few episodes. So what I'm going to do is write this as following. This is stress, U. Okay. And here I'm going to write another thing. Now I need to tell you something else before I can write this hysteresis. I want to tell you that the HPA axis so this is depression. Cortisol causes depression, and depression elevates cortisol. So it's both ways. What do I mean to say? 50% of people with major depression disorder have high cortisol and large adrenal. So and a lot of other dysregulations in the HPA axis. So people with depression a lot of times have high cortisol and high adrenal. These are the people we're going to discuss. You can say maybe that's because they have stress. Of course, depression is horrible psychological stress, sometimes described as an internal battle. A person might be sitting on the edge of their bed, but inside is coiled with a heroic psychological battle to put on their pants or clothes or something. Right? So that might be the explanation, but it's also the other way around. So depression might cause the high cortisol, but also high cortisol by itself causes depression. How do we know that? If you have a tumor in the adrenal that secretes cortisol, that's called Cushing's disease. You have so much cortisol. Classically, what it does is make you have this kind of Cushing body shape, which is a lot of fat, like a round fat shape and round face and fat here. So there's a kind of a Cushing phenotype. And many people with Cushing's disorder have major depression as a side effect of the high cortisol. Also, if you take steroids, which are analogs of cortisol, for example, if you have autoimmune disease and you need to reduce the immune system, you take steroids, or edema, if you have a brain tumor and there's a lot of fluid in the brain, you want to reduce it, you take steroids, high level steroids for months. A big side effect is depression. And also, stopping cortisol synthesis can cure or alleviate depression, even though that's not used right now as a drug because it has a lot of side effects. So we know that depression leads to high cortisol, but high cortisol itself leads to depression in some people, probably people with some genetic susceptibility to depression that it's not understood yet. So what we can draw on this axis here is the adrenal size. As a measure, a biological measure, let's say, for depression, where low adrenal mass is the normal state and high adrenal mass is depressed state, at least for that 50% of depression that has high adrenal. And so let's agree that. So what is this diastasis? In physics, this is called hysteresis. It looks like this. You start with a normal adrenal, and as you increase stress, the adrenal increases. Why? Because increased stress, there's more X1, so pituitary grows, there's more X2, so adrenal grows. That's why when you increase stress, the adrenal grows. That's normal. But then something amazing happens. You jump at a certain stress level to high adrenal. Okay? You jump to high adrenal. Now, if you lower the stress, you don't jump right back. You lower the stress, you're stuck on this high adrenal line, and you have to go much lower to go back to normal. So this is depression, and this is normal. Our normal neurotic moody selves, let's call it like that. That's something like what psychiatrists describe in depression. Okay, any questions about this concept of hysteresis? So Alfredo asks, does the mania phase vary across bipolar individuals or is similar? So mania is more stereotyped than depression, and mania looks very similar. And a psychiatrist colleague of mine who studies bipolar says that people with bipolar can run a big company or be homeless, really different support systems, sure. But when they have mania, they clinically look very similar. That's why mania is thought to be more stereotyped. Depression, there are a lot of, you can either be sleeping too much or too little. You can be hyperactive or low active. There's a lot of differences in depression. And Ronnie Stock says, do the other 50% of people with major depression have no physiological differences? So as I said, 50% have high cortisol. There's another fraction, let's say 20% that have what's called atypical depression, and they have the opposite problem. They have too low adrenal, too low cortisol, and that causes a lot of weakness and kind of like chronic fatigue. So that's atypical depression. They have the opposite problem with their adrenal cortex, so it could be too high or too low. And then there's some with normal HPA, and they have a different issue probably. So hope I answered your question. So this concept of hysteresis, we're going to try to understand this concept of hysteresis. How does it happen? All right. So how does it happen? So what we're going to do is I'm going to add some more biological information now about major depression. There's another physical change seen in people that have high adrenal major depression, and that is that certain brain areas are damaged. For example, I told you the major depression associated with memory problems, and that is because there's area in the brain called hippocampus. We're going to call it small h. That's located quite near the hypothalamus in the lower middle part of the brain. That's responsible for memories and short-term memories, and then passes them to the cortex for long-term storage. And it also has a very important regulatory role on stress. So you can say that the hippocampus inhibits the stress signal. So you can say that U should be U divided by H or something like that, where H is like some measure of the activity of the hippocampus. If we make a huge simplification to take a complicated brain region and just summarize it by one activity, the more active the hippocampus, the lower your stress signals. And the reason for that is because memories can tell you that a situation is actually safe or control the amygdala and cortex regions of the brain that sense stress. And my favorite example of that is, in the 1890s, there was this, or in the 18th century, when there was the first movie showed to the public, which was of a train coming. So some reports are that the audience saw the train coming and got out of this and panicked and ran out in great stress. Nowadays, we sit, and if we see the same movie, we wouldn't even dream of getting up and running because we know it's just a movie, right? How do we know it's just a movie? Because our brain can interpret reality in a different way from those in the 19th century, in the 1800s. And the same stimulus gives us a different perception. And so if you hurt the hippocampus, you basically stop inhibiting a lot of stress signals, and there's extra stress signals. You can see that. And when I say hippocampus, I'm going to also include the prefrontal cortex, which also plays a role. In humans, it's very important. In mice and rodents, mostly the hippocampus that plays this role. But so H will be the activity of these brain regions. And the interesting thing is that cortisol, our friend cortisol, it basically destroys the hippocampus. And also in humans, the prefrontal cortex region, it binds to a receptor called glucocorticoid receptor. Glucocorticoid receptor is found in the brain primarily in the hippocampus and in the prefrontal cortex in humans. And cortisol does three bad things to the hippocampus. First of all, it kills neurons. Second, it shrinks the connections or synapses, the connections between neurons. And third thing, it stops the birth of new neurons. And in the last 20 years or so, it's become evident that most of the brain, the neurons don't divide or aren't formed, but in the hippocampus is one place where new neurons are made in a certain region. So cortisol stops that. So cortisol in rodents, high stress just shrinks the hippocampus synapses very quickly and slowly just kind of atrophies the hippocampus. In human beings with many depression bouts, you can see of the volume of the hippocampus decrease on average by 20%. It's not, this H is not the volume, it's the activity. Apparently, chronic stress hurts memories and the hippocampus and prefrontal cortex activities quite badly. So we can be quite confident of that these two arrows exist, even though the details are far from being like clear exactly what's, especially in humans, what region is doing what. So there's 5 new messages. Wow, that's great. Yeah, cortisol helps waking up. So why can't people get out of bed? So cortisol, remember, everything about cortisol is biphasic. At low levels, you're very tired. At high levels, you're very tired. In the middle, you're energized, right? So depression takes you to the too high level. Yeah. The effect of U on A is not immediate. How long do you need to be under high stress in order for the jump to occur? Right, correct. So this jump, as we'll see, takes weeks. So you need to be under stress for weeks. Are people with past depression more sensitive to develop depression in the future? Correct. People with past depression are more sensitive to develop depression in the future. Part of it is irreversible damage to H. That's part of the reason. Yeah. So it's getting stressed might get you out of normal depression. Okay, normal depression is high cortisol, but there's atypical depression, which is low cortisol. So there you might say getting stressed, or let's call it stimulated, might be a way to help get out of the atypical depression. I hope so it's in fact too high. So let's remember that cortisol and let's say activity or looks like this. So here we have the major depression we're talking about. Here we have the atypical depression. Here we have optimal stimulation. Like when you're in flow, etc. When your PhD project is going so well, you can't believe it. You're at the edge. You were born to do this. You're in the right place with the right people, doing the right thing. That's how this feels like. This is a song by Michael Elowitz about during his PhD in Princeton. It's morning in the grad school. I'm a little more depressed. Each morning it's a bit more tired. Trouble getting dressed. When first I came to grad school, I thought it would be fun. But after 3 years in the lab, I've yet to see the sun. But maybe today will be different. My experiment, my work, who knows? I might get hot. I might discover something interesting. I might make a little more progress. I might meet a beautiful postdoc. But then again, I might not. This is part of this is actually the opening song from our musical tragedy about a PhD that we performed in Princeton in the 1990s, 1999 or so. Maybe I'll do more songs for you from the musical tragedy later. Okay, so that's about cortisol and depression. How do we measure the effect? How does one measure the effect of hippocampus on you? So that's a huge question, and there's definitely ways nowadays to optically make mice that optically, where you can with light, with an optical fiber, activate their hippocampus and measure, let's say, the effect on X1 CRH, so that there's differently possible to do that. And there's lots of experiments like that show these wirings, also just direct wirings from hippocampus to, let's say, the amygdala and the hypothalamus, with all kind of inhibitory neurons. So there's anatomical and physiological ways to measure that. Yeah. So what about patients who have hippocampus removed? So patients with hippocampus removed have huge stress, because imagine what it's like to need to operate in the world without short-term memories. You need to reinvent your story all the time, and I don't know what happens to their cortisol levels, but that's maybe that information exists. Yeah, acute cortisol also affects the brain, and actually in good ways. It kind of, so everything I said is biphasic. So acute stress makes this focus your attention, and it makes memories more salient, so you actually remember more. So it's all this biphasic effect. Like a medium amount of cortisol is very good, and a high and long amount of cortisol is destructive. This could actually also be an anti-mutant. Do you remember we had this biphasic thing to remove mutants of beta cells that sends too much glucose? If a neuron has this GR receptor and it's mutated so that it senses too much cortisol signal, it could be that there's a signal to kill that neuron, because it's probably a mutant. It can't be that cortisol is so high for so long. And you might also ask, why should the good nature give us this terrible destruction of the hippocampus? So evolutionary biologists think that depression can have a selective advantage in this following situation. So this is studies by Sapolsky on baboons. When a baboon attacks the alpha male and loses, they often go to the side and can't get up in the morning, and they're kind of depressed for days and weeks. And the evolutionary reason, he thinks, is that if that baboon continued to attack the alpha male, that baboon would be killed. So it's kind of it's as if when your stress is so high, it's as if you shut down, you stay at home, and maybe wait till the hard times have passed, or stop a destructive behavior or something like that. That's like the argument why you have this circuit. It's like a defense mechanism. All right. Okay, so that's enough talking. Now let's do some dancing. No. So what can we do to understand this hysteresis effect? So what I'm going to show you now is that if you have a system where you activate the HPA axis, and the HPA axis inhibits something that inhibits the HPA axis, that situation can be summarized as following. We have the adrenal and the hippocampus activity, and the adrenal that makes cortisol shuts down the hippocampus activity, and the hippocampus shuts down the input to the adrenal, as I said. So on the slow time scale, we have this circuit, which in systems biology is called a toggle switch. Toggle switch, which means either A is large and H is small, or H is large and A is small. They inhibit each other. It's actually a positive feedback loop made of two negatives. And this circuit we're going to explore together. So how do we do that? Okay, so hippocampus. And I'm going to talk about drugs towards the end. I'm just going to say that many of you might have heard of Prozac and its many other names. Did you hear of Prozac? Imagine. So these drugs are effective for 30 to 50% of people with depression. Some people, those drugs don't help. The thing is that they work on neurotransmitters, and they work very quickly within hours, and they also have side effects very quickly. But on depression, you have to take them for like weeks, 4 weeks, 6 weeks before you see an effect. So this time scale of weeks is also mysterious because they work on neurotransmitters so quickly, but it takes such a long time to work on depression. They can actually make depression worse in the beginning sometimes. And so the time scale, why do drugs like SSRIs take a month to work? Something we want to understand. Or, all right, so these kind of dynamics. Maybe I'll tell you how these SSRI work. The current theory about depression is that it has to do with a certain kind of neurotransmitters in the brain, the dopamine, serotonin, and noradrenaline. And the best drug right now, these SSRIs, this is neuron 1, this is neuron 2. And the way that these synapses work is that neurons 1 secretes the neurotransmitter that goes into neuron 2 and causes an electric spike. This is, let's say, serotonin. And these SSRIs, selective serotonin reuptake inhibitors, they work to increase the serotonin in the following way. There are pumps that pump back the serotonin into the cell, reuptake, and the drug, SSRI, inhibits that pump. And so it increases serotonin in the synapse. And for some reason, that has a positive effect on depression. Within hours, the serotonin levels rise, but it only takes weeks for depression to get better. One of the things that serotonin does, it helps the hippocampus. So SSRIs that increase serotonin, they make the hippocampus more active, they make neurons divide more, etc. So it's like acting, among many other things, also at the hippocampus level too. So that we're going to understand the drugs like that. I hope I was clear about SSRIs and Prozac, etc. Okay, so we have SSRI. We have the toggle switch. Okay, now I'm going to erase this SSRI, depression, cortisol. So, and I'm going to write down some equations right now, and I'm going to do it quickly. So don't be discouraged if you can't follow me. You'll see everything in the lecture notes. My goal, where I'm going for, is to make our face portrait like we do in this course. On the axes are the adrenal size and the hippocampus. So I want to get some null clines. So what do I mean by null clines? If I set a certain amount of hippocampus, so I set H, what's going to happen to A? So we know that high hippocampus, a lot of hippocampus activity inhibits A. So this is this null cline. Okay? This is the dA dt equals 0 null cline. Steady state A when I fix H activity. And then I want the other null cline, which is what happens when cortisol inhibits H through this glucocorticoid receptor. And the important thing about glucocorticoid receptor is that it's very cooperative. So X3, and this is GR activity. It's really cooperative at some threshold. It works like, let's say cortisol doesn't kill neurons there unless it's a kind of all or none, unless it's a very, very large amount of cortisol. And so if I write an equation for hippocampus activity, I have some production of hippocampus. By the way, it's not C times H, it's just C because these neurons come from stem cells. It's not the neurons divide, it's stem cells divide to provide neurons at some rate C. And they're also destroyed. So they're destroyed at rate A. And then this function. So this function of X3, a function that looks like this, drops. So if we want to get this null cline, I have to solve this equation. I get that H equals, so I move this C divided by A, or C divided by A plus B. It depends if cortisol is less than the threshold or cortisol is larger than the threshold. Because if cortisol is less than the threshold, GR is basically 1, and I have I have so what did they do here? Yeah, right. So when cortisol is large, we have when we have high cortisol, we have higher removal. Yeah, right. Okay, that's fine. So when cortisol is large, we have higher. Oh, I drew this the opposite way. Of course. The killing, let's say, the killing of neurons is high only when cortisol is high. That's why I got confused. Sorry about that. So if cortisol is high, you have more killing. If cortisol is low, you have less killing. And so this curve, this null cline looks like this. It starts at C over A, and then it drops to C over A plus B at some threshold adrenal where cortisol is larger than K. So these are what these null clines look like. And you can see that there's a single fixed point here, which has high H and low adrenal. And this is the normal state where you have a lot of hippocampal activity and relatively low HP activity, normal HP activity, and everything is fine. Okay. Now I'm going to tell you that, in fact, these parameters can change between people. So if I have a person that's prone to depression, this B could be larger. And we can have this situation. So in this person, there's, let's say, maybe mutations in the system for the glucocorticoid receptor, and those mutations are, in fact, one of the genetic risk factors for depression. And now you see there's 3 fixed points. This is the normal fixed points, and this is the depression fixed point. Because why? Because it has high adrenal and low H. High adrenal, low H. And maybe we start life here in this area here, and we don't get to this depressed state. Okay. Nadav says, we assume that all hippocampus activity makes adrenal decrease, or maybe it depends on the hippocampus activity type. Yeah, absolutely. So hippocampus is a brain region with huge, it's like very, very complex, and it has to do with spatial orientation and reason. It's like very, very important. And so this is such a huge simplification. So here we're discussing the ability of the hippocampus to inhibit the HPA axis. That we'll call that H. Again, is a big simplification. And now we want to understand this hysteresis. So what we're going to do is we're going to turn on stress. So what does stress do? Stress activates the HPA axis. So stress makes more X1, which makes P grow, makes more X2, that makes A grow. So stress increases A. And we can see that stress pushes, so for a given amount of hippocampus, if I have more stress, I'm going to have a larger A. So stress does this. And now maybe you can see where I'm going. So what is stress doing? It's increasing my A. Increasing my A, like that. But if I have even more stress, this, I now come to a situation where I've lost this fixed point. So at very high stress, I have only one fixed point, only one fixed point. So instead of 3 fixed points, stable, unstable, stable, I now have only one. And now what happens is that I flow to this only one fixed point with high adrenal. So over weeks, I flow and I reach this point with high adrenal and low H, which is the depressed state. It's kind of a super depressed state. And now, suppose stress goes back to normal. I'm here, and I flow back to this fixed point because I'm now on the low branch. In fact, there's an important line in this phase plot, which is called separatrix, that separates all the initial conditions that flow to one fixed point and all the initial conditions that flow to the other fixed point. So if I was here and now I return to the original stress level, I'm below the separatrix and I flow to the depressed state. And I'm stuck there. Now if I reduce stress, I'm still up here. I have to reduce stress all the way down to here so that this is the only fixed point, and then I flow back. So I have to go down to much lower levels of stress in order to go back, to escape this doom of being in the depressed part of the phase of the null clines. And that's what the toggle switch does. It and if the parameters are right and you have 3 fixed points, stress can make adrenal increase slowly, and then this fixed point is gone. There's only one fixed point. The separatrix doesn't apply anymore because it only applies to the original unstable fixed point. Then you flow to the original, to the depressed state. And now if stress returns back, you flow, you're below the separatrix, you flow to this state. And you have to remove stress very much in order to lose the depressed fixed point and have, again, only one normal fixed point. So that's kind of a way to think about this situation of why it's so easy to get into depression, but so hard to get out of it. For some people with certain parameter sets, it's easy. Other people, it could be that this null line doesn't intersect 3 points, and you never get depressed, basically. You just don't have that possibility. How does sport help with depression? Sport is a serious antidepressant, and I'm blanking out on the answer right now. Maybe if somebody knows, one of my students or something, you can type in the answer. But okay, so we're going to clean this up. And write it again. So we have our adrenal and our hippocampus. We have one null line where the higher hippocampus is, the smaller the adrenal for a given stress level. And we have the other null line, which is the higher the adrenal, at a certain level, boom, it destroys the hippocampus. And giving us 3 fixed points: stable, unstable, stable. And suppose we have a person who's in depression right now. So the person is right here. Major depressive disorder. High adrenal and low H. High cortisol, etc. What about these SSRIs? So the SSRIs help production of hippocampal neurons and activity. So we're going to add them here. S plus C. So more SSRIs. Let's say more hippocampal activity and regeneration. Now, if we want to compute the null line, it's going to be S plus C divided by A, or S plus C divided by A plus B, if X3 is greater than K, and if X3 is lesser than K. So this, what it does is it basically lifts the null line, the hippocampus null line. So adding the drug lifts the null line. And if you add enough of it, okay, so this is SSRI, then you lose the depressed fixed point. And again, you have only one fixed point, this one. And so you're here. And now you start moving back towards the healthy state. And once you're in the healthy state, you can take away the drug. You go back to this fixed point and find things are fine. In fact, you only have to take the drug so long as your dynamics cross the separatrix of the original null line, of the original phase space. Because then, if you stop taking the drug, you're inside the basin of attraction and you still flow to the healthy state. I hope I was clear here. That the separatrix only exists for a certain amount of alkaline. So when I take the drugs, the separatrix is no longer there. But when I stop taking the drugs, I go back to the original system, and the separatrix tells me. So if I was here, now I'm going to flow to here, to the healthy fixed point. So, but if you keep taking the drug, you're in this high H, low A situation. Again, everything is paradoxical. When you take SSRIs, it actually activates the HPA axis. So you get even more cortisol on the short time scale. But on the long time scale, it normalizes down cortisol. So it's, again, everything is like different when you do acute and chronic. But anyway, the dynamics here take weeks, and that's why that's our answer. Why SSRI takes a month to work is because, according to this theory, you need to change the activity of H and the size of A into the basin of attraction of the normal fixed points. Okay. Why do people with depression usually have to continuously take the medication? After we brought them back to the good fixed point, can't they theoretically stop taking the med? So I think so, at least in the beginning, you can stop taking the med and be okay. But if you've had a lot of damage to your hippocampus over years, irreversible damage, it could be that it's impossible now to raise this. You might have such damage. It's not possible anymore to get rid of this fixed point because of damage to the hippocampus. It's irreversible, and that's a possibility. Or SSRIs only work for 30 to 50% of the population. As said. Another solution is what's called ECT, this electroconvulsive therapy, which is a strong electric currents pass through the brain when you're anesthetized. And that's also done over a period of weeks to protect actually memories and stuff like that. Also somehow jolts the system back to the normal state. Not clear how that works at all. And of course, psychotherapy. So cognitive behavioral therapy, the way one might interpret that is that it acts on your perceptions, and that can lower your stress. So it could actually move stress below this low threshold and cure you. So CBT, cognitive behavioral therapy, meditation, all these things are non-pharmacological ways to deal with depression. And of course, it's very good to have a combination of pharmacology and psychotherapy, meditation, relaxation, vacation, all those Asians that reduce stress into the relaxed nation. So we can just relax. I want to love you. I want to hold and treat you right. I want to love you every day, and it's relaxing things. Now that we understand how stress fits in, if you have someone in depression around you, this relaxation, meditation, psychotherapy, unless of course there's a situation which is intractable, and then there's actually people in depression spend decades in the back wards of psychiatric hospitals in a catatone state. And they are sometimes even have to go removal of the hippocampus, for example, in order to. But that's extremely extreme medication or disconnect parts of the cerebral cortex. There's all kind of surgeries like that for severe intractable cases. And there's also postpartum depression, which is actually the first kind of depression after birth where HPA medicine, a kind of HPA antagonist taken for weeks, is shown to be effective. And there's a history of HPA drugs for depression. A lot of them didn't work or had a lot of side effects, but now there's a drug for postpartum depression that apparently is working. And I think there's a lot of potential here, but we have to understand the dynamics properly in order to treat. What's the implications of a high H under SSRI? I don't know. I'm not sure. I'm not sure about that. Yeah, so first, is it realistic to model bipolar behavior with limit cycle oscillation? It's possible because inside the HPA, there's a negative, there's an oscillator, and another positive feedback loop on top of that can cause what's called limit cycle oscillations, where you toggle from A to H to A to. So that's a possibility that's worth exploring, I think, Alfredo. Even though in the last lecture we talked about bipolar disorder as noise-driven oscillations around a spiral fixed points where you don't need an additional positive feedback loop. So that's an interesting question. It's good for me. Oh, 4 new messages. So Itai says DMT is a rapid-acting drug that deals with depression. Is that true? How does it explain? Can you just say what is DMT? Itai? The blue line. Yeah. While Itai is writing what is DMT, a fast-acting drug. Oh, I think I remember now, but can you write it anyway? So the blue line is called separatrix. Separatrix is a very important concept. So suppose we have our situation. This is the two null lines. We have stable fixed point and a stable fixed point and an unstable one in the middle. Separatrix separates this plane into points that all points here flow here, and all points below the separatrix flow here. So it's separates the phase plane to let's say the normal fixed point. So this is the basin of attraction to the normal fixed point. Another side here is basin to the depressed fixed point. So this is this area, and separatrix is the border between them. So if we take drugs or something, and our system moves here, and now we stop taking drugs, we go back to these null lines, and the separatrix says, "Oh, we're in the normal stable of attraction, basin of attraction." So that's why it's important. And so this is a ayahuasca-related drug. Itai says dimethyltryptamine. Yeah, I don't know the answer. It's actually really cool if somebody could look up. There's also another drug that's fast acting that has to do with a sedative. And I can't remember right now. So those drugs are beyond this model. I don't know. I can't explain what they do, and maybe it relates, and maybe it's something different. Yeah. Itai, if you have any idea, that would be very interesting. You know, in the end of this course, you know, you're going to choose a research project, so that could be a cool one. All right. So I think it's a good time to wrap up. If you have any more questions, this is the time to write. What time is it now? Masha. Yeah, finish early. I'm at the top of the world, I'm looking down on creation, and the only explanation I can find is the love that I found ever since you were around. You're what kept me at the top of the world. Thank you for taking hormone circuits. It's so satisfying to get your questions and exercises. By the end of the course, I hope you'll learn a lot about ordinary differential equations, about hormones and how they connect. And you'll have a final project when you can explore your favorite question, whether it's depression or elation, it's up to you. So see you next week, where we continue our exploration of hormone circuits. Bye-bye.